Welcome to the Deep Sleep Science channel. Tonight, we're going to take a slow and gentle journey through one of the most powerful forces in the universe, gravity. The same invisible force that quietly holds you to the Earth is also the force that keeps the moon circling our planet, the planets orbiting the sun, and entire galaxies drifting together through space. It is everywhere, always working, yet almost completely silent. Gravity is the natural attraction between objects that have mass. Anything with mass, from a grain of dust to a giant star, pulls on everything around it. The more massive something is, the stronger its gravitational pull becomes. Distance also matters. The closer two objects are, the stronger that pull becomes. Because of this simple rule, gravity organizes the universe into systems: moons around planets, planets around stars, and stars gathered into galaxies. On Earth, gravity gives weight to everything around us and pulls objects downward at about 9.8 meters per second squared. But gravity behaves differently across the solar system. On the Moon, it is only about 1/6 as strong, which is why astronauts could hop so easily across its surface. On giant planets like Jupiter, gravity is far stronger, while on small, icy worlds like Pluto, it is incredibly gentle. Gravity does more than simply pull objects together. According to Einstein's theory of general relativity, gravity is actually the bending of space-time itself. Massive objects like stars and planets curve the fabric of space around them, and other objects move along those curves. Even light follows these bends, which is why distant galaxies can appear warped or magnified through a phenomenon called gravitational lensing. Across the universe, gravity builds and shapes nearly everything we see. It gathers clouds of gas into stars, pulls planets together from dust and ice, creates tides in oceans, and guides the motions of galaxies over billions of years. It can also produce some of the most extreme events in existence, such as neutron stars, black holes, and ripples in spacetime known as gravitational waves. Yet despite its immense power, gravity works slowly and steadily, creating balance and order across unimaginable distances. From the quiet rhythm of ocean tides to the motion of galaxies millions of light years away, gravity is the calm architect of the cosmos. So tonight, as we explore these relaxing facts about gravity and space, we'll drift through planets, stars, black holes, and distant galaxies, discovering how this simple force quietly shapes the entire universe. Around us, gravity is the force that draws masses toward one another, and it works everywhere in the universe, from a falling object near Earth to the motion of entire galaxies. The strength of this pull depends on two main things: how much mass the objects have and how far apart they are. Bigger objects create a stronger pull, while greater distance weakens it. This simple rule helps explain motions on Earth, the behavior of planets, and the structure of the cosmos itself. In Einstein's general relativity, gravity is not described as an invisible rope or push between objects. Instead, mass and energy curve space-time, and objects move through that curved geometry. In a gentle way, this means that planets orbit stars because they are following the shape of space-time around them. It is a deeper picture of gravity than the older idea of force alone. Massive objects can bend the path of light because they warp space-time around them. Even though light has no rest mass, it still follows the curved structure created by gravity. So when light passes near something very massive, like a galaxy or black hole, its path can be changed. This is one of the most beautiful and surprising predictions of modern physics. That bending of light is known as gravitational lensing. It acts a little like a natural cosmic lens, except it is created by gravity rather than glass. When astronomers observe this effect, they can study objects that are very far away, or too faint to see clearly otherwise. It turns gravity itself into a tool for observing the distant universe. Gravitational lensing can magnify extremely distant objects that would otherwise be too dim for detailed study. A massive foreground galaxy or cluster can brighten and enlarge the light from something lying far behind it. This allows astronomers to glimpse galaxies from earlier periods of cosmic history. In a quiet way, gravity helps us look deeper into time. Einstein rings appear when a distant source, a massive foreground object, and the observer line up very closely. In that special geometry, the bent light forms a ring or near ring around the closer object. These rings are rare because the alignment must be very precise. When they are found, they provide especially rich information about gravity and the mass of the lensing object. Strong gravitational lenses can create arcs, multiple images, or nearly complete rings from a single background source. What looks at first like several separate objects can actually be one distant galaxy whose light has taken different paths around a massive body. These patterns help astronomers measure hidden mass, including matter that gives off no light. Gravity can therefore reveal what the eye alone could never see. General relativity predicts that time passes more slowly in stronger gravity. This means that a clock deep in a gravitational field ticks a little more slowly than one farther away. The effect is tiny in everyday life, but it is real and measurable. Gravity does not only shape motion and light, it also shapes time itself. Atomic clock experiments have confirmed that clocks at lower elevations tick slightly more slowly than clocks at higher elevations in Earth's gravitational field. Even a difference in height on the same planet changes the passage of time by a tiny amount. These experiments bring Einstein's ideas out of theory and into direct measurement. Something as familiar as altitude quietly affects the rate at which time moves. GPS depends on extremely precise timing, so the effects of gravity and motion must be corrected for the system to work properly. Satellites high above Earth experience time a little differently from clocks on the ground. If engineers ignored those differences, positioning errors would build up quickly. So every day, modern navigation depends on relativity being true. The sun's gravity is what holds the solar system together. Every major planet, dwarf planet, comet, and asteroid follows paths shaped mainly by the sun's enormous mass. Without that central gravitational anchor, the solar system would not have its ordered structure. The calm regularity of planetary motion begins there. The sun is the largest object in the solar system, and because of that, its gravity dominates the motions of the planets. It contains the overwhelming majority of the solar system's mass. That is why Earth goes around the sun, and why the other planets do as well. The scale of the sun's influence is immense, even at the far edges of the planetary system. Gravity compressed the sun's core until pressure and temperature became high enough for hydrogen fusion to begin. That fusion is what powers the sun's light and heat. Inward gravitational squeeze and outward energy pressure exist in a long balance. In this way, gravity helped create the star that makes life on Earth possible. NASA states that the sun converts about 4 billion kilograms of mass into energy every second through fusion. This sounds enormous, and it is, yet the sun is so massive that it can continue shining for billions of years. The energy released this way is what radiates outward as sunlight. Gravity made the conditions for this steady transformation possible. A normal star remains stable because inward gravity is balanced by outward pressure from hot gas and fusion in the core. Gravity is always trying to compress the star, while the energy from fusion pushes back. As long as those two influences remain balanced, the star stays in a stable phase. Much of a star's life is a long, quiet negotiation between collapse and pressure. When a star's core fuel begins to run low, gravity starts to gain the upper hand, and the core begins to contract. This contraction can raise temperatures and trigger new stages of fusion, depending on the star's mass. Eventually, gravity drives the star into later phases of evolution. So even the aging of stars is guided by gravity. Gravitational waves are ripples in space-time itself. They are produced when massive objects accelerate in especially violent ways, such as when black holes or neutron stars orbit and merge. Instead of traveling through space like sound through air, they are tiny distortions of space-time moving outward. They carry information about events that may be impossible to observe clearly in any other way. Einstein predicted gravitational waves in 1916 as part of general relativity. For a long time, they remained a theoretical idea because the effect is so incredibly small by the time it reaches Earth. Detecting them required instruments of extraordinary precision. Their eventual discovery became one of the great achievements of modern science. LIGO made the first direct detection of gravitational waves from merging black holes. That observation confirmed a major prediction of Einstein's theory and opened a new way of studying the universe. Instead of only seeing the cosmos through light, scientists could now also listen to it through gravitational signals. It marked the beginning of gravitational wave astronomy. The first detected signal, called GW 150,914, came from a black hole merger in a distant galaxy. Two black holes spiraled together, collided, and became one larger black hole, releasing energy in gravitational waves. By the time the signal reached Earth, the stretching and squeezing it caused was unimaginably tiny. Yet it was still detected with care and precision. Black holes are not empty holes in the usual sense, but extremely dense concentrations of matter packed into a very small region. Their gravity becomes so strong that it changes the behavior of space, time, and light in dramatic ways. They are formed through extreme gravitational collapse. They are among the clearest examples of what happens when gravity becomes overwhelming. The event horizon is the boundary around a black hole beyond which nothing can escape. It is not a wall or shell, but a point of no return in space-time. Once something crosses that boundary, every possible path leads further inward. The concept is simple, but its implications are profound. Even light cannot escape from inside the event horizon. That is why black holes appear black. Since light is the fastest thing known and still cannot get out, the region within the event horizon is hidden from outside view. Gravity there has become so extreme that escape is no longer possible. Matter falling toward a black hole can be heated, stretched, squeezed, and torn apart by powerful tidal forces. The closer it gets, the greater the difference in gravity from one part of the object to another. This can distort stars or clouds of gas into long streams. In some cases, this process releases brilliant radiation before the material disappears. The popular term spaghettification refers to this stretching caused by extreme gravitational gradients near a black hole. One part of an object can be pulled much more strongly than another, creating a long, thin distortion. Though the name sounds playful, the physics behind it is very serious. It is an example of gravity acting unevenly across an object. Near a black hole, time also behaves strangely according to relativity. To a distant observer, processes close to the black hole may appear slowed by strong gravity. This effect is another reminder that gravity is not just about falling or pulling. It changes the very rhythm of time. White dwarfs are the remains of low and medium-mass stars after they have exhausted much of their nuclear fuel. They no longer produce energy through the same core fusion as before, yet they remain stable because of quantum mechanical pressure. They are small, dense, and incredibly compact. They show how gravity can compress a star without turning it into a black hole. A typical white dwarf is about as massive as the Sun, but only slightly larger than Earth. That means a huge amount of matter is packed into a remarkably small volume. The result is a star remnant of extraordinary density. It is one of the clearest demonstrations of how strongly gravity can compress matter. A white dwarf's surface gravity can be about 100,000 times stronger than Earth's. On such an object, the pull downward is so strong that its atmosphere is compressed into a very thin layer. Heavier elements tend to sink beneath lighter ones because gravity sorts them efficiently. It is a calm but powerful example of gravitational order. Neutron stars form when massive stars collapse and explode as supernova. After the outer layers are blasted away, the remaining core can be crushed by gravity into something far smaller and denser than a white dwarf. In that state, matter is compressed to extremes beyond ordinary experience. These objects are among the densest known in the universe. Gravity compresses more mass than the Sun's into a neutron star only about city-sized across. Imagine something with the mass of a star squeezed into a body small enough to compare with a metropolitan area. The density becomes almost beyond intuition. Gravity has pushed matter into one of its most extreme stable forms. Pulsars are rotating neutron stars observed through their beams of radiation. As they spin, those beams sweep across space, and if Earth lies in the path, astronomers detect regular pulses. This is why pulsars can seem almost like cosmic lighthouses. Their precise timing makes them valuable natural laboratories. Some pulsars spin thousands of times per second. That means an object with more mass than the Sun can rotate with astonishing speed while remaining stable. Such rapid spinning reflects the conservation of angular momentum during stellar collapse. Gravity shrinks the star, and the rotation can become dramatically faster. Strong gravity near neutron stars bends light paths, so astronomers can sometimes see emission from regions that would otherwise remain hidden. The curvature of space-time near the star redirects light in subtle ways. This means observations can reveal more than a simple straight-line view would allow. Once again, gravity becomes part of how we see. Our solar system travels around the center of the Milky Way at roughly 515,000 miles per hour. Even though we do not feel this motion in everyday life, Earth, the Sun, and the rest of the solar system are all part of that grand orbit. Gravity from the galaxy keeps this long journey in motion. We are not standing still in the cosmos, but moving through it constantly. One orbit of the solar system around the center of the Milky Way takes about 230 million years. That means the dinosaurs lived during a very different location in the galaxy than we do today. A single galactic year is far longer than human history. Gravity guides this slow, majestic motion on a truly enormous scale. The motions of planets, moons, asteroids, and comets are controlled mainly by gravity. Though these objects vary widely in size and composition, the same underlying law governs them all. Their paths may be circular, elliptical, stable, or chaotic, but gravity is the main organizer. It gives structure to what might otherwise be cosmic wandering. Planetary orbits remain stable over long periods because moving objects keep falling around the Sun rather than straight into it. A planet has forward motion, while the Sun's gravity constantly pulls it inward. The result is a curved path that continues again and again. Orbit is, in a sense, a beautifully balanced kind of falling. The Moon's gravity is the main driver of Earth's ocean tides. As the Moon pulls on Earth, ocean water is redistributed into broad bulges. These bulges move relative to coastlines as Earth rotates. The result is the familiar rise and fall of sea level that has shaped shorelines and human life for ages. Tides are really a repeating redistribution of Earth's ocean water, not a simple piling up in one place. Water shifts across the planet in response to gravitational differences, and Earth's rotation carries coastlines through these moving patterns. So tides are global motions rather than isolated local events. The whole ocean system participates in this rhythm. The Moon's gravity slightly distorts not only Earth's oceans, but also the solid body of Earth. The ground itself rises and falls a little under tidal forces, even if we do not notice it directly. So tides are not just about water. Gravity gently flexes the planet as a whole. Earth's shape is stretched slightly by lunar gravity, becoming a little elongated. This stretching is very small, but it is real and measurable. The Moon's pull is stronger on the near side of Earth than at the center, and weaker still on the far side. That difference is what creates the overall distortion. Earth has two main tidal bulges, one on the side facing the Moon and one on the far side. The near side bulge forms because the Moon pulls more strongly there, while the far side bulge forms because the Moon pulls less strongly there than it does on Earth's center. This often surprises people, but it follows naturally from the differences in gravitational pull across the planet. It is a subtle and elegant effect. The sum also affects Earth's tides, even though the Moon has the stronger tide-raising influence because it is much closer. The Sun is vastly more massive, but its greater distance reduces its tide-producing effect. Even so, solar gravity still matters greatly. Earth's tides are shaped by both neighbors in the sky. Spring tides happen when the Sun, Moon, and Earth line up. In that arrangement, the gravitational effects of the Sun and Moon reinforce one another. This creates especially large differences between high and low tide. Despite the name, spring tides are not connected to the season of spring. Neap tides happen when the Sun and Moon pull at right angles relative to Earth. In this geometry, their tide-producing effects partly counteract one another. The result is a more moderate tidal range. High tides are not as high, and low tides are not as low. The Moon is tidally locked, so the same side always faces Earth. This happened because over long periods, gravitational forces slowed the Moon's rotation until it matched its orbital period. As a result, one lunar hemisphere always looks toward us, while the other remained unseen until spacecraft explored it. Gravity can synchronize motion with great patience. Evidence suggests that many exoplanets are tidally locked with their stars. On such worlds, one side may face permanent daylight, while the other stays in endless night. This kind of locking is especially expected for planets orbiting close to their stars. It shows that gravity can shape not only motion, but also climate and habitability. Lagrange points are places where the gravitational effects of two large bodies combine in a useful way. At these positions, a smaller object can maintain a relatively stable relationship with the two larger ones. They are not gravity-free places, but rather special solutions within gravity. They are deeply important in spaceflight and astronomy. In the Sun-Earth system, there are 5 Lagrange points. Each has its own geometry and usefulness. Some are more stable than others, and some are better suited for scientific spacecraft. Together, they show that gravity can create pockets of balance within larger motion. The James Webb Space Telescope operates near Sun-Earth L2, about 1.5 million kilometers from Earth. This location allows Webb to remain in a favorable arrangement relative to Earth and the Sun. It gives the telescope a stable thermal environment and a clear view into deep space. A carefully chosen gravitational location makes extraordinary observation possible. L4 and L5 are special among the Lagrange points because they are resistant to gravitational perturbations. Small objects placed there tend to remain more naturally stable than at some other points. dust and asteroids can even gather in these regions. In a quiet way, gravity creates natural harbors in space. Gravitational lensing helps astronomers map dark matter because matter bends light whether it shines or not. Dark matter does not emit or reflect light in the usual way, but its gravity still affects the path of light traveling through space. By studying distortions in background galaxies, astronomers can infer where that hidden mass lies. Gravity becomes a way of drawing maps of the invisible. The same physical law that causes an apple to fall also governs planetary motion, tidal cycles, black hole mergers, and the bending of light. Gravity works across ordinary human scales and across the largest known structures in the universe. It does not need one rule for Earth and another for galaxies. Its reach is both familiar and immense. Taken together, modern space research shows gravity as both an organizer and a transformer. It builds stars and planets, shapes moons and tides, guides spacecraft, bends light, slows clocks, and powers some of the most extreme events in the universe. It is one of the quietest forces in daily life, yet one of the most powerful on the cosmic stage. In nearly every direction we look, gravity is there, patiently shaping the story. The Newtonian gravitational constant, usually written as the letter G, describes how strong gravity is in the universe. Its measured value is about 6.67430 times 10 in standard scientific units. This number is extremely small, which explains why gravity between everyday objects like books or chairs is so weak that we never notice it. But when enormous amounts of mass are involved, such as planets, stars, or galaxies, even this small constant produces powerful effects that shape the structure of the cosmos. On the surface of Earth, the acceleration caused by gravity is about 9.80 meters per second squared. This means that when an object falls freely near the ground, its speed increases by about 9.8 meters per second every second. This steady acceleration is what causes a dropped object to fall faster and faster as it descends. It also explains why the weight we feel is really the result of Earth's gravity pulling us toward its center. Mercury's surface gravity is about 3.70 meters per second squared, which is much weaker than Earth's gravity. Because Mercury is smaller and less massive than Earth, its gravitational pull is reduced. If a person could stand on Mercury, they would feel much lighter than they do on Earth. The lower gravity would also allow objects to fall more slowly and travel farther when thrown. Venus has a surface gravity of about 8.87 meters per second squared, which makes it surprisingly similar to Earth's gravity. Even though Venus is slightly smaller than Earth, its mass is close enough that the gravitational pull on its surface feels quite familiar. If humans could stand safely on Venus, they would feel almost the same weight as they do on Earth. This similarity is one of the reasons Venus is sometimes called Earth's twin, though the two planets are very different in other ways. Mars has a surface gravity of about 3.71 meters per second squared. This is only a little more than 1/3 of Earth's gravity. On Mars, a person would weigh much less than they do on Earth, and jumping or lifting objects would feel easier. The weaker gravity also affects the planet's atmosphere, making it difficult for Mars to hold a thick atmosphere over long periods of time. Jupiter's equatorial surface gravity is about 24.79 meters per second squared, which is more than twice as strong as Earth's gravity. Jupiter is enormously massive, containing more mass than all the other planets combined. Even though it is made mostly of gas rather than solid rock, its powerful gravity still dominates the surrounding region of space. This immense pull influences moons, rings, and even distant asteroids throughout the solar system. Saturn's equatorial surface gravity is about 10.44 meters per second squared. This may sound surprising because Saturn is far larger than Earth. However, Saturn is made mostly of hydrogen and helium and is much less dense than rocky planets. Its enormous size spreads its mass over a larger radius, which reduces the surface gravity compared with what we might expect. Uranus has a surface gravity of about 8.87 meters per second squared, almost the same as Venus. Although Uranus is much larger than Earth, its density is lower because it contains large amounts of ice and gas. This balance between mass and size results in gravity that feels fairly similar to Earth's. If someone could stand on Uranus, their weight would not feel dramatically different. Neptune's surface gravity is about 11.15 meters per second squared, slightly stronger than Earth's gravity. Neptune is a massive, icy giant planet with a strong gravitational pull. Despite being much farther from the Sun than Earth, its gravity still plays an important role in shaping the orbits of its moons and nearby objects. The planet's gravitational influence extends across a wide region of the outer solar system. Earth's escape velocity is about 11.19 kilometers per second. Escape velocity is the speed an object must reach to break free from a planet's gravitational pull without needing additional propulsion. Rockets leaving Earth must eventually reach this speed if they want to travel into deep space. The stronger a planet's gravity, the higher the escape velocity required. Jupiter's escape velocity is about 60.20 kilometers per second, the highest among the planets in our solar system. Because Jupiter is so massive, escaping its gravity requires extraordinary speed. A spacecraft leaving Jupiter would need to move far faster than one leaving Earth. This powerful gravity is one reason Jupiter has been able to capture and hold dozens of moons. Mercury's escape velocity is about 4.25 kilometers per second. Because Mercury is small and has relatively weak gravity, objects can escape from it much more easily than from Earth. This low escape velocity also makes it harder for Mercury to hold onto an atmosphere. Over time, gases that might have formed an atmosphere were lost to space. Mars has an escape velocity of about 5.03 kilometers per second. This value is higher than Mercury's but still much lower than Earth's. The relatively weak gravity of Mars is one reason its atmosphere became thin over billions of years. Gases could escape more easily into space compared with a planet with stronger gravity. Neptune's escape velocity is about 23.56 kilometers per second. This high value reflects the planet's significant mass and gravitational strength. Even though Neptune is far from the Sun, its gravity still holds onto a thick atmosphere and a system of moons. Escaping Neptune's gravitational pull would require a spacecraft to reach very high speeds. When an object falls, it accelerates because gravity continues to pull on it during the entire fall. The force of gravity does not stop acting once the object begins moving. Instead, gravity keeps increasing the object's speed as it moves downward. This is why falling objects speed up steadily until air resistance begins to slow the acceleration. In a vacuum, gravity causes objects of different masses to fall at exactly the same rate. This surprising result means that a heavy rock and a small pebble would hit the ground at the same time if there were no air to slow them down. The mass of the object does not change how gravity accelerates it. This principle was famously demonstrated during experiments on the Moon. Feathers and hammers appear to fall at different speeds on Earth because of air resistance. The feather experiences much more drag from the air, which slows it down. In a vacuum, where there is no air to create drag, the feather and hammer fall together. This simple demonstration helps show that gravity pulls equally on all masses. Astronauts on the International Space Station appear to float because they are in continuous freefall around Earth. The station is moving forward very fast while gravity pulls it downward. This combination causes the station and everything inside it to keep falling around the planet instead of straight toward it. As a result, astronauts experience weightlessness. About 90% of Earth's gravity still exists at the altitude of the International Space Station. Many people imagine that gravity disappears in space, but that is not the case. Gravity becomes weaker with distance, yet it remains quite strong even hundreds of kilometers above Earth. The feeling of weightlessness is caused by orbiting, not by the absence of gravity. The term microgravity is used instead of zero gravity to describe the environment in orbit. Tiny forces still exist inside spacecraft, such as vibrations, air movement, and small accelerations. These forces are extremely small compared with gravity on Earth. That is why astronauts experience a condition that feels almost weightless. Scientists estimate that microgravity aboard the International Space Station is roughly 1/1,000,000th the strength of Earth's gravity. This environment allows researchers to perform experiments that would be impossible on Earth. Liquids, flames, crystals, and biological systems behave differently when gravity's influence is greatly reduced. These studies help scientists understand physics and biology in new ways. The Sun's gravity dominates the solar system because it contains the vast majority of the system's mass. Every planet, comet, and asteroid is influenced by the Sun's pull. Without that central gravitational anchor, the solar system would not remain organized. Instead, objects would drift unpredictably through space. Gravity gathered gas and dust together to form the Sun billions of years ago. As the material collapsed under its own weight, pressure and temperature increased in the center. Eventually, the core became hot enough to ignite nuclear fusion. In this way, gravity helped create the star that lights and warms our planet. A star remains stable because two powerful forces balance each other. Gravity pulls inward, trying to compress the star, while energy from nuclear fusion pushes outward. When these forces are equal, the star maintains its size and brightness for long periods. This delicate balance can last for billions of years. When the fuel in a star's core begins to run low, gravity slowly starts to win the battle against outward pressure. The core contracts and heats up, sometimes triggering new stages of fusion. These changes can transform a star into a giant, or eventually into a stellar remnant. Gravity therefore guides a star through every phase of its life. The Sun is roughly halfway through its main sequence lifetime. It has been shining for about 4.6 billion years and is expected to continue doing so for several billion more. During this long period, the balance between gravity and fusion keeps the Sun stable. This stability has allowed life to develop on Earth. Gravity controls the motion of planets, moons, asteroids, and comets throughout the solar system. Every one of these objects follows paths that are shaped mainly by the gravitational pull of larger bodies. The Sun provides the strongest influence, but planets also affect one another in subtle ways. Over long periods of time, these gravitational interactions create the orderly structure we observe in the solar system today. Planetary orbits remain stable because objects in motion keep falling toward the Sun while also moving sideways through space. Instead of falling straight inward, their sideways motion causes them to follow curved paths. These paths repeat again and again, creating the elliptical orbits described by Kepler's laws. In a simple way, orbiting can be understood as continuous falling that never quite reaches the ground. Orbits that are closer to Earth move faster because gravity becomes stronger at shorter distances. Satellites in low Earth orbit must travel at high speeds to remain in orbit rather than falling back to the surface. The closer they are to the planet, the faster they must move. This relationship between distance and orbital speed is a fundamental rule of orbital mechanics. A satellite such as NASA Aqua spacecraft circles Earth roughly once every 99 minutes. At that altitude, the spacecraft must move at tremendous speed to maintain its orbit. Each orbit allows the satellite to collect valuable information about Earth's atmosphere, oceans, and climate. Gravity keeps the satellite in its curved path, while its forward motion keeps it from falling directly downward. A satellite placed in geostationary orbit takes about 23 hours, 56 minutes, and 4 seconds to circle Earth. This period matches Earth's rotation relative to the stars, allowing the satellite to remain above the same point on the surface. From the ground, the satellite appears almost motionless in the sky. This special orbit is extremely useful for communication and weather monitoring. A geostationary satellite appears fixed over one location on Earth because its orbital motion matches Earth's rotation. As the planet turns, the satellite moves along with it at exactly the right speed. This synchronization allows antennas on the ground to point toward a single position in the sky without needing to track the satellite. The arrangement relies entirely on precise gravitational balance. Geostationary orbit can only exist above Earth's equator. This is because the satellite must orbit in the same plane as Earth's rotation. If the orbit were tilted, the satellite would appear to move north and south in the sky. By remaining above the equator, the satellite stays aligned with Earth's spin. Polar-orbiting satellites travel over the north and south poles as Earth rotates beneath them. Each orbit passes over a different region of the planet. Over time, the satellite eventually scans nearly the entire surface of Earth. This type of orbit is especially valuable for mapping, weather observation, and environmental monitoring. The Moon's gravity is the primary cause of tides in Earth's oceans. As the Moon pulls on Earth, water shifts across the planet's surface. The side of Earth facing the Moon experiences a slight bulge of water. Another bulge forms on the opposite side because the gravitational pull there is weaker than at Earth's center. Tides are not simply water rising in one place and falling in another. Instead, they represent a constant redistribution of ocean water across the planet. Earth rotates through the tidal bulges, causing shorelines to experience changing sea levels. This slow rhythm has shaped coastal ecosystems and human activities for thousands of years. The Moon's gravitational pull also slightly distorts the solid body of Earth. The planet itself rises and falls by small amounts as tidal forces act on it. Although these changes are tiny compared with ocean tides, they can still be measured with sensitive instruments. Gravity therefore flexes both land and sea. Earth becomes slightly stretched due to the Moon's gravitational pull. This stretching creates a shape that is a little longer in the direction pointing toward the Moon. The difference is extremely small but measurable. Such distortions demonstrate how even distant objects can influence our planet. Earth has two tidal bulges, one facing the Moon and one on the opposite side. The near side bulge forms because the Moon's pull is strongest there. The far side bulge forms because the Moon pulls less strongly on that side than it does on Earth's center. These differences in gravitational pull across Earth create the familiar tidal pattern. Most coastlines experience 2 high tides and 2 low tides each day. As Earth rotates through the tidal bulges, sea level rises and falls. This repeating cycle happens roughly every 12 hours. The rhythm of tides has influenced navigation, fishing, and coastal life for centuries. The time between one high tide and the next is usually a little more than 12 hours. This interval occurs because Earth rotates beneath the tidal bulges created by the Moon's gravity. As the planet turns, coastlines move into and out of these regions of higher water. The result is the regular rise and fall of ocean levels. High tides are not usually located directly under the Moon. Earth's rotation moves the tidal bulges slightly ahead of the Moon's position. This small shift occurs because friction between the oceans and the seafloor drags the water forward. Even small forces can shape large systems when they act continuously. Because the Moon moves along its orbit, Earth must rotate about 50 extra minutes before the same location aligns with the Moon again. This is why the timing of tides changes slightly each day. Coastal communities notice that high tide occurs later each day by roughly this amount. The shifting schedule reflects the Moon's motion through space. The Sun also contributes to Earth's tides, even though it is much farther away than the Moon. Its enormous mass still creates a noticeable gravitational effect. While the Moon has the stronger tidal influence, the Sun's gravity can strengthen or weaken tidal patterns. The interaction between these two forces creates the full tidal cycle. The Sun's tide-raising effect is a little less than half as strong as the Moon's. Even though the Sun is vastly more massive, its distance reduces its tidal influence. Distance plays a powerful role in determining gravitational strength. This balance between mass and distance explains many patterns in the solar system. Spring tides occur when the Sun, Moon, and Earth line up in a straight or nearly straight line. During this alignment, the gravitational pulls of the Sun and Moon combine. This produces especially high tides and very low tides. Despite the name, spring tides can occur during any season. Neap tides occur when the Sun and Moon are positioned at right angles relative to Earth. In this configuration, their tidal forces partly cancel one another. The result is smaller differences between high and low tides. The ocean still moves, but the changes are more moderate. Spring tides typically occur during the new moon and full moon phases. At these times, the Sun, Earth, and Moon lie along merely the same line. Their combined gravitational pull produces stronger tidal effects. The pattern repeats roughly every 2 weeks. Neap tides occur during the first quarter and last quarter phases of the Moon. In these phases, the Sun and Moon form a right angle with Earth. Their gravitational influences partially oppose each other. This produces the gentler tidal conditions associated with neap tides. Earth's gravity also creates tides on the Moon itself. Although the Moon has no oceans, its rocky surface still experiences tiny shifts. Earth's gravitational pull slightly stretches and compresses the Moon. These changes are small but measurable. Laser measurements show that Earth's tidal pull can move parts of the Moon's surface by about 10 to 15 centimeters. Scientists bounce laser beams off reflectors left on the Moon by Apollo missions. By measuring tiny changes in distance, they can detect these small movements. This technique provides extremely precise information about lunar motion. Earth's gravitational pull helps shape certain features on the Moon's surface called lobate scarps. These are small cliffs formed by the Moon slowly shrinking as it cools. Tidal forces from Earth may influence how these features develop. Even across the distance between Earth and the Moon, gravity leaves its mark. The Moon is tidally locked to Earth, meaning the same side always faces our planet. Over time, gravitational forces slowed the Moon's rotation until it matched its orbital period. As a result, one hemisphere constantly faces Earth, while the other remains hidden from direct view. This is why early observers could only see one lunar side. Most large moons in the solar system are also tidally locked with their planets. This means they rotate once for every orbit they complete. The process occurs because gravitational forces gradually slow a moon's rotation. Over long periods, this synchronization becomes stable. Large moons can become tidally locked relatively quickly in astronomical terms. In some cases, this can happen within hundreds of thousands of orbits. Once the rotation slows enough to match the orbital period, the locked state tends to remain stable. gravity quietly locks the motion into place. Many exoplanets close to their stars are expected to be tidally locked as well. One side of such a planet may face constant daylight, while the other remains in darkness. This extreme difference could affect the planet's atmosphere and climate. Gravity again shapes the environment in subtle ways. The Moon's surface gravity is about 1/6 of Earth's. Because the Moon is much smaller and less massive, its gravitational pull is weaker. Objects weigh far less there than on Earth. This difference strongly affects how movement and exploration occur on the lunar surface. Apollo astronauts appeared to hop and bounce while walking on the Moon. The weaker gravity allowed them to move in ways that would be impossible on Earth. Their steps carried them farther and higher with each push. Watching the footage gives a clear visual example of how gravity changes movement. The Moon has 3 main internal layers: a crust, a mantle, and a core. These layers formed as the Moon cooled and its materials separated by density. Heavier elements sank toward the center, while lighter materials rose toward the surface. Gravity played an essential role in this process of planetary differentiation. Billions of years ago, the Moon was molten. During that time, gravity caused heavier materials to sink toward the center, while lighter materials floated upward. This sorting process helped create the layered structure observed today. Many planets and moons formed through similar gravitational processes. Earth's core contains about 30% of Earth's mass, while the Moon's core accounts for only about 1.6 to 1.8% of the Moon's mass. This difference reflects the materials from which the Moon formed. It contains less iron and heavy metals than Earth. Gravity sorted the materials differently during formation. The Moon formed from debris produced during a massive collision early in Earth's history. Much of that debris contained less iron than Earth itself. As a result, the Moon ended up with a smaller metallic core. Gravity helped gather the debris into a single spherical body. The Moon is far enough away that the other 7 major planets could fit in the space between Earth and the Moon. The average distance between the 2 bodies is about 384,000 kilometers. Although it appears close in the night sky, the Moon is actually quite far away. This distance allows both bodies to orbit safely without colliding. Mercury is the smallest planet in the solar system and only slightly larger than Earth's Moon. Because of its small size, Mercury has weaker gravity than Earth. This affects its ability to hold an atmosphere and influences its surface environment. The planet's gravity shapes everything from its geology to its thin exosphere. Mercury is also the fastest planet, completing one orbit around the Sun in just 88 Earth days. Being so close to the Sun means Mercury experiences strong solar gravity. Its rapid motion reflects the intense gravitational pull it feels at that distance. The closer a planet is to the Sun, the faster it must travel to remain in orbit. Mercury's small size means its gravity is not strong enough to hold a thick atmosphere. Over billions of years, most gases escaped into space. As a result, Mercury's surface experiences extreme temperature differences. Gravity again determines what a planet can keep and what it loses. NASA Messenger mission orbited Mercury for more than 4 years and greatly improved our understanding of the planet. Before that mission, Mercury was still one of the least understood worlds in the inner solar system. By circling the planet again and again, Messenger measured its surface, magnetic field, chemistry, and internal structure in far more detail than before. This showed how gravity and careful orbital tracking can help scientists learn what lies inside a planet they cannot directly open or inspect. Scientists studying data from Messenger found evidence that Mercury's inner core is solid. This is important because Mercury is a small planet, and for a long time researchers were still working out how its interior was arranged. By using precise measurements of rotation and gravity, they were able to infer details about the core deep inside the planet. It is a good example of how gravity can reveal the hidden structure of a world from afar. Venus is Earth's closest planetary neighbor in the solar system. Although Mercury is sometimes closer on average in certain orbital calculations, Venus is commonly described this way because its orbit lies just beyond Earth's, and the two planets are very similar in size. Venus and Earth are often compared because they are both rocky worlds with nearly the same diameter. But despite this closeness, Venus turned out to be one of the most hostile planets in the solar system. Venus rotates very slowly and in the opposite direction from most planets. This means that if you could stand on its surface and watch the sky, the sun would appear to rise in the west and set in the east. Its strange rotation makes Venus unusual among the major planets. Scientists think this odd motion may have resulted from ancient collisions or long-term atmospheric and gravitational effects. Venus has surface gravity close to Earth's, even though Venus is a little smaller. That means a person standing on Venus would feel a weight not very different from what they feel on Earth. This is one reason Venus seemed at first glance like it might be somewhat Earth-like. But similar gravity does not mean similar living conditions, because almost everything else about Venus is far more extreme. Venus is hotter than Mercury, even though Mercury is closer to the Sun. The reason is not simply distance, but atmosphere. Venus has a tremendously thick atmosphere rich in carbon dioxide, which traps heat very effectively through a runaway greenhouse effect. So even though Mercury receives more direct sunlight, Venus holds onto heat far more efficiently. The Pioneer Venus mission used radar to map Venus's surface through its thick cloud cover. Visible light cannot easily show the ground there because the planet is permanently hidden beneath dense clouds. Radar, however, can pass through that cloud layer and bounce off the surface. This allowed scientists to begin building a clearer picture of Venusian mountains, plains, and other landforms. Pioneer Venus confirmed that Venus's clouds are made mainly of sulfuric acid. These are not soft water clouds like many of Earth's clouds, but highly corrosive clouds made from very different chemistry. This discovery helped show just how alien Venus really is. Even its sky is shaped by harsh chemical conditions, unlike those on Earth. According to Pioneer Venus findings, Venus has little, if any, global magnetic field. Earth's magnetic field helps protect our atmosphere from some of the charged particles coming from the Sun. Venus, by contrast, lacks a strong planet-wide magnetic shield of the same kind. This difference may have played an important role in how the planet's atmosphere evolved over time. Mars's lower gravity helps explain why giant volcanoes like Olympus Mons could grow so large. On Earth, stronger gravity pulls down more heavily on tall mountains and volcanoes, making it harder for them to reach extreme heights before collapsing or spreading out. On Mars, the weaker pull allows enormous structures to remain standing more easily. This shows how a planet's gravity can directly shape its surface. NASA says Olympus Mons rises more than 25 miles from base to summit. That makes it the largest volcano and one of the tallest known mountains in the solar system. Its enormous size is possible partly because of Mars's weaker gravity, and partly because Mars lacks the kind of plate tectonics that would move the volcanic region around. Gravity and geology together helped create something truly vast. A detailed gravity map of Mars showed that spacecraft can be pulled off ideal paths by huge mass concentrations such as Olympus Mons. Even though spacecraft are carefully guided, they still respond to slight differences in a planet's gravitational field. Massive volcanic regions and buried structures can create measurable variations. This means gravity maps are not only useful for science, but also for navigation. Mars's lower gravity and shallow slopes would make Olympus Mons easier to climb than its tremendous size might suggest. Although it is incredibly tall, its slopes are spread across a very wide area. On a human scale, the incline is often gentle compared with steep mountains on Earth. So the volcano is huge in height, but not necessarily dramatic in steepness at every point. Jupiter is the largest planet in the solar system. Its diameter is so large that Earth looks small beside it, and its mass is greater than that of all the other planets combined. Because of this, Jupiter has an enormous gravitational influence over the rest of the solar system. It is not just a big planet, but a major gravitational power. If Jupiter were hollow, roughly 1,000 Earths could fit inside it. This comparison helps people picture just how enormous Jupiter really is. Even though it is not hollow, the statement gives a strong sense of its scale. Size alone does not tell the whole story of gravity, but in Jupiter's case, both size and mass are extraordinary. Jupiter's massive gravity helps shape asteroid orbits throughout the solar system. The asteroid belt lies relatively close to Jupiter in cosmic terms, so many small bodies there feel its pull over long stretches of time. This influence can change their paths, create gaps in the belt, or send some bodies into new regions. Jupiter acts like a giant gravitational sculptor. Close encounters with Jupiter can knock asteroids out of the main belt and redirect them across the solar system. A passing asteroid that comes near enough can have its orbit changed significantly without ever colliding with the planet. This process has helped move material between different parts of the solar system over billions of years. Gravity can therefore send small bodies on entirely new journeys. Jupiter's Great Red Spot has enough mass concentration in its winds to measurably alter Juno's speed during a flyby. This is remarkable because it means a storm system in an atmosphere can produce a detectable gravitational effect on a spacecraft. The storm is not just visually impressive, but massive enough to affect motion. It shows how gravity can help scientists probe even deep weather systems. Juno measured tiny Doppler shifts in its radio signals to estimate the depth of the Great Red Spot. As the spacecraft flew near Jupiter, the storm's mass slightly changed Juno's speed, and that small change affected the radio signal. By studying those minute differences, scientists could infer how far down the storm extended. This is a subtle and elegant use of gravity as a scientific tool. NASA reports that the Great Red Spot extends roughly 300 miles below Jupiter's cloud tops. That means this famous storm is not just a shallow surface feature, but a deep atmospheric structure. It reaches far downward into Jupiter's thick gaseous layers. Gravity-based measurements helped reveal the hidden depth of something that had long been known mainly for its appearance. Jupiter's gravity gave both Voyager spacecraft a free speed boost towards Saturn. This is a classic example of a gravity assist, sometimes called a slingshot maneuver. By passing near Jupiter in just the right way, the spacecraft gained energy and speed without using huge extra amounts of fuel. Gravity here became not an obstacle, but a partner in exploration. Saturn is made mostly of hydrogen and helium. These are the same light elements that make up most of the Sun, though Saturn never became massive enough to ignite fusion like a star. Its composition helps explain its low density and giant size. It is a world where gravity gathered vast quantities of light material into a single enormous planet. Saturn is the only planet with an average density lower than water. This does not mean it could literally float in a giant ocean, since no such ocean could exist, but it does show how low its overall density is. Much of Saturn is made of light gases rather than dense rock or metal. This unusual property helps explain why such a large planet can still have surface gravity only moderately stronger than Earth's. Saturn's surface gravity is only a bit stronger than Earth's, even though Saturn is vastly larger. This seems surprising at first, but the explanation is that gravity at the surface depends not only on mass, but also on distance from the center. Saturn's great size spreads that mass over a larger radius. So a much bigger planet does not always mean crushingly stronger surface gravity. Saturn's rings are made mostly of water ice. This is why they reflect sunlight so well and appear bright through telescopes. Although they look smooth from far away, they are actually made of countless separate particles orbiting Saturn together. Gravity keeps this magnificent system arranged in thin, flat bands. The particles in Saturn's rings range from smaller than grains of sand to objects as large as mountains. So the rings are not made of one uniform type of material or one single size. They are a complex collection of icy pieces of many scales, all orbiting under Saturn's gravitational control. What looks like a simple band is actually a crowded and detailed structure. Saturn's ring system is so broad that, from one side to the other, it would not fit in the distance between Earth and the Moon. This comparison helps show how enormous the rings are across their width. At the same time, they are often surprisingly thin compared with that width. Gravity has arranged a structure that is vast sideways, yet delicate vertically. Saturn's 7 main rings are labeled D, C, B, A, F, G, and E in the order they were discovered. The lettering does not run alphabetically outward from the planet because the names reflect discovery history rather than a neat geometric sequence. Each ring has its own characteristics, thickness, brightness, and particle distribution. Together they form one of the most recognizable sights in the solar system. NASA research indicates that Saturn is losing ring material as icy dust rains into the planet under the combined effects of gravity and magnetic influences. Tiny particles can be pulled inward rather than remaining in stable ring orbits forever. This means the rings are not a permanent structure frozen in time. Gravity can build beauty, but it can also slowly take it apart. Cassini gravity data suggest that Saturn's rings may be much younger than Saturn itself. Saturn formed billions of years ago, but the rings may have formed far more recently from shattered moons or disrupted icy bodies. By using gravity measurements, scientists estimated the mass of the rings and gained clues about their age. So even one of the most iconic features in the solar system may not be ancient in its present form. Titan's gravity was used repeatedly by the Cassini spacecraft to reshape its orbit around Saturn. Each close flyby changed Cassini's path in a controlled way, allowing mission planners to send it to new locations in the Saturn system. This made Titan not just an object of study, but also a gravitational partner in the mission. Gravity assists can work inside planetary systems as well as between planets. A final Titan gravity assist sent Cassini onto its impact course into Saturn. This last maneuver was carefully designed so the spacecraft would burn up in Saturn's atmosphere, rather than risk contaminating moons like Titan or Enceladus. Even the end of the mission depended on precise gravitational planning. Titan's pole helped guide Cassini to its final destination. Uranus rotates at a tilt of about 90 degrees, so it appears to spin on its side. Most planets rotate more upright relative to their orbit, but Uranus is dramatically different. This means its poles and equator take turns facing the Sun in unusual ways over the course of its long year. Its strange orientation may have been caused by giant impacts early in its history. Uranus is very cold and windy. Even though it is not the farthest planet from the Sun, it has an unusually low internal heat output compared with some other giant planets. Its atmosphere still experiences strong winds and active weather patterns. It is a distant, pale world shaped by gravity, gas, cold, and long seasons. Uranus has faint rings and more than 24 moons. These features make it a complex planetary system in its own right, not just a simple blue-green ball in the distance. The moons and rings are all held and organized by Uranus's gravity. Even in the far outer solar system, gravity creates order on many scales. Neptune was the first planet discovered with mathematics before it was directly seen. Astronomers noticed that Uranus was not moving exactly as expected, and they realized another unseen object's gravity might be disturbing its orbit. By calculating where that hidden planet should be, they predicted Neptune's location. This was one of the great triumphs of gravitational reasoning. Neptune is the most distant major planet from the Sun. Because of that, it receives far less sunlight than Earth does, yet it remains an active and dynamic world. Its great distance also means its orbit is slow, taking about 165 Earth years to complete one trip around the Sun. Even so far out, the Sun's gravity still holds it firmly in the planetary system. Triton is Neptune's largest moon. It is a fascinating world in its own right, with a unique orbit and evidence of geologic activity. Neptune's gravity dominates Triton's motion, but Triton also carries clues about the distant outer solar system. It is not just another moon, but one of the most unusual large satellites known. Triton is the only large moon in the solar system that orbits opposite to its planet's rotation. This kind of orbit is called retrograde. Most major moons move in the same direction their planets spin because they formed from the same surrounding material. Triton's backward motion strongly suggests a different history. Scientists think Triton is a Kuiper belt object that was captured by Neptune's gravity. The Kuiper belt is a distant region beyond Neptune filled with icy bodies. If Triton formed there and was later captured, that would explain why it behaves differently from typical large moons. Gravity can sometimes adopt wandering objects into new planetary families. Triton's retrograde orbit is one of the main reasons scientists consider capture the most likely explanation for its origin. If Triton had formed naturally around Neptune from a disk of material, it would probably orbit in the same direction Neptune rotates. Instead, its backward orbit points to a more dramatic past. Gravity again preserves a record of history and motion. Neptune's gravity is slowly drawing Triton inward over time. The interaction between Triton and Neptune is not completely static. Tidal forces gradually change the orbit, causing the Moon to move closer over immense spans of time. Orbital systems can evolve slowly for billions of years under the steady influence of gravity. Millions of years from now, Triton may get close enough to Neptune to be torn apart by gravitational forces. If it crosses a critical distance, the difference in gravity across the Moon could become too strong for the Moon to hold itself together. This process is related to what scientists call the Roche limit. A moon that now appears stable may eventually be destroyed by the same gravity that holds it. If Triton is torn apart, it could form a bright ring system around Neptune. The broken pieces would continue orbiting the planet, spreading into a broad ring structure. In that case, Neptune might one day have a ring system even more striking than the faint one it has now. Gravity would transform a moon into a new kind of beauty. Pluto's gravity is only about 6% of Earth's. This means a person standing on Pluto would weigh far less than they do here. The weak gravity affects how easily gases escape, how surface materials behave, and how the atmosphere changes over time. Small worlds often reveal clearly how much gravity matters. Pluto's low gravity allows its thin atmosphere to extend much higher above the surface, in relative terms, than Earth's atmosphere does. Because the pull downward is weaker, gas molecules can spread farther outward. This gives Pluto an atmosphere that behaves very differently from the one surrounding Earth. Gravity influences not just whether an atmosphere exists, but also its shape and reach. When Pluto moves far from the Sun, much of its atmosphere may freeze out and fall back to the surface as snow or frost. Far from the Sun, temperatures become so low that gases can condense into solid form. Later, when Pluto moves closer again, some of that material can return to the atmosphere. This makes Pluto's atmosphere part of a slow seasonal cycle, driven by temperature and weak gravity. Pluto is smaller than Earth's moon. This can surprise people because Pluto was once classified as a planet and still feels large in the imagination. In reality, it is a small, icy world in the outer solar system. Its size helps explain its low gravity and the unusual behavior of its thin atmosphere. Pluto and Charon orbit a common center of gravity that lies in the space between them. This point is called a barycenter, and in this case, it is outside Pluto itself. That is unusual for a planet-moon pair. Rather than one body simply circling inside the larger one's pull, both move around a shared point in space. Because Pluto and Charon orbit around a barycenter located between them, they form an unusually balanced binary-like system. Charon is large enough compared with Pluto that the two bodies behave more like partners than a typical planet and small moon. Their motion is a beautiful reminder that gravity is always shared between bodies, even when one is larger. Some systems are so evenly balanced that this shared dance becomes especially clear. New Horizons measured Pluto at about 370 kilometers in diameter. That helped settle a long-standing question about Pluto's exact size and showed that it is slightly larger than some earlier estimates suggested. Precise measurements like this matter because size connects directly to gravity, density, and internal structure. Knowing Pluto's diameter more accurately allows scientists to better understand what kind of world it really is. Charon was measured at about 208 kilometers in diameter. That is very large compared with Pluto itself, which is one reason the Pluto-Charon system is so unusual. Charon is not a tiny moon beside a dominant planet, but a major companion with a significant share of the system's total mass. Its size helps explain why the two bodies orbit a point in space between them. Pluto's surface ices can sublimate directly into gas when Pluto moves closer to the Sun. Sublimation means a solid changes straight into gas without first becoming liquid. Because Pluto is so cold, substances like nitrogen, methane, and carbon monoxide can behave in ways unfamiliar on Earth. This gives Pluto a seasonally changing atmosphere linked to sunlight, temperature, and weak gravity. The solar system has more than 890 known moons. That number reflects not just the large moons people often hear about, but also many smaller, irregular moons discovered around the giant planets and beyond. The growing count shows how active planetary discovery still is. Each moon is another example of gravity holding objects together in long-term orbital relationships. Many asteroids and trans-Neptunian objects also have moons held by their gravity. Even relatively small bodies can sometimes capture or retain companions if the conditions are right. These small moon systems help scientists study how collisions, capture events, and orbital evolution happen. They show that gravity does not need a giant planet to create a partnership in space. Some minor bodies have such weak gravity that landing on them can be much harder than landing on a larger world. On a big planet, gravity pulls the spacecraft downward and helps keep it settled on the ground. On a tiny asteroid or comet, a spacecraft can bounce, drift, or even escape again if it touches down too forcefully. Weak gravity creates a very different kind of engineering challenge. The Moon's surface resists impacts better than Bennu's loose surface because the Moon's gravity is much stronger. On the Moon, material is held down more firmly, so the surface behaves differently when struck. Bennu, by contrast, has such low gravity that surface material can be loosely packed and easily disturbed. This means landing or sampling operations can produce unexpected results on very small bodies. Bennu returned a pristine sample rich in carbon, nitrogen, and organic compounds. This made the mission especially important because such materials are closely connected to the chemistry of the early solar system. Studying them can help scientists understand how the building blocks of planets, and possibly life, were distributed long ago. Gravity helped preserve that ancient material inside a small body over vast spans of time. Earth's gravity will significantly alter Bennu's path during its close flyby in 2135. Even without a collision, a close planetary encounter can change an asteroid's future orbit. This happens because Earth's gravity will tug Bennu as it passes by, slightly changing its speed and direction. Over long periods, even a small change like that can matter a great deal. A tiny region called a gravitational keyhole could, in principle, place Bennu on an impact trajectory for a later century, though the chance is extremely small. A keyhole is a very small region in space, such that if an asteroid passes through it during a close flyby, gravity redirects it onto a future collision path. This idea shows how sensitive orbital motion can be. A slight change during one encounter can influence events far in the future. Small body orbits can be changed by close planetary encounters even when no collision occurs. A world does not need to physically hit an asteroid or comet to alter its course. Gravity alone can bend the path, speed it up, slow it down, or place it into a different orbit. This is one of the reasons the solar system remains dynamic rather than frozen. Rosetta became the first spacecraft to orbit a comet. This was an extraordinary technical achievement because comets are small, irregular, and weak in gravity compared with planets. Orbiting one required careful navigation in a very delicate gravitational environment. The mission turned a moving comet into a place that could be studied closely over time. Rosetta's target, Comet 67P/Churyumov-Gerasimenko, has such low gravity that landing there was extremely challenging. On a world that small, a spacecraft cannot rely on strong downward pull to hold it in place. Even a gentle touchdown can become unstable. The mission had to be designed with the strange physics of very weak gravity in mind. Philae bounced after touchdown partly because the comet's gravity is so weak. Instead of settling immediately onto the surface, it rebounded and moved again before finally coming to rest. On Earth, or even the Moon, that kind of bounce would be much more limited. On a comet, low gravity can turn landing into something more like a cautious contact than a firm arrival. Rosetta scientists used the way the spacecraft was pulled by the comet's gravity to estimate the comet nucleus's porosity. By tracking how the spacecraft moved, they could infer how much mass the comet had and how that mass was distributed. Combining that with the comet's size let them estimate how much empty space existed inside it. Gravity thus became a way to measure how loosely packed the comet really was. A comet's small gravity also means its gas and dust environment can strongly influence nearby spacecraft operations. When sunlight warms the comet, material can stream away from its surface. Around such a weakly bound object, those jets and particles can have a noticeable effect. In that setting, gravity is not the only influence on motion, and engineers must account for both. Asteroids, comets, planets, and moons all formed from material gathered together by gravity in the early solar system. Tiny grains and larger pieces of matter collided, stuck together, and slowly built larger bodies. Over time, gravity helped turn clouds of debris into worlds. The immense variety we see today began with gravity patiently assembling material. In the outer solar system, gravity pulled ices and gases together to form the giant planets. Far from the Sun, temperatures were low enough for volatile substances to remain solid or icy, giving those growing worlds access to more material. Once they became massive enough, their gravity could pull in large amounts of gas as well. This helped create worlds like Jupiter, Saturn, Uranus, and Neptune. Space agencies use gravity not only to study worlds, but also to travel between them. Rather than fighting gravity all the time, mission designers often use it strategically. By carefully planning trajectories, they can let planets and moons reshape a spacecraft's path. Gravity becomes both a scientific subject and a practical tool. A gravity assist can add or subtract orbital energy from a spacecraft. Depending on the direction and geometry of the flyby, the spacecraft may speed up, slow down, or change direction. It is not getting energy from nowhere, but exchanging it with the moving planet or moon. This makes gravity assists one of the most elegant methods in space navigation. Gravity assists are a major reason distant missions can be flown without impossible amounts of fuel. Reaching the outer solar system directly would often require launch energies beyond what many missions can realistically carry. By borrowing energy through flybys, spacecraft can go farther than their fuel alone would otherwise allow. This has made many historic missions possible. The effect of a gravity assist works by exchanging momentum with a moving planet or moon. The planet is so massive that the change to its motion is tiny and practically undetectable, while the spacecraft can gain a meaningful difference in speed. It is a subtle interaction, but extremely useful. A small vehicle can ride the motion of a giant world. In practical terms, a spacecraft can tap into a planet's enormous orbital angular momentum during a flyby. This does not mean the spacecraft steals motion in a simple, everyday sense, but rather that the geometry of the encounter allows part of the planet's motion around the Sun to influence the spacecraft's path. It is one of the clearest examples of orbital mechanics being used with precision and imagination. Mariner 10 was the first mission to use a gravity assist to change its flight path. This marked an important step in space exploration, showing that planetary flybys could be more than close observations. They could also become part of the route itself. That idea later became central to many ambitious missions. Mariner 10 used Venus's gravity to reach Mercury. Without that flyby, reaching Mercury would have been much harder because of the demands of inner solar system travel. Venus helped bend and reshape the spacecraft's path in just the right way. Gravity from one planet made exploration of another possible. Cassini needed 4 gravity assists to get to Saturn because no available launch vehicle could send it there directly on the required path. That mission was far too ambitious to rely on brute force alone. Instead, mission planners designed a long and clever route that used several worlds as stepping stones. Gravity served as part of the propulsion strategy. Cassini's cruise trajectory included flybys of Venus, Earth, and Jupiter. Each encounter adjusted the spacecraft's speed or direction, gradually shaping the path toward Saturn. The journey was long, but it was efficient and carefully planned. It showed how a spacecraft can move through the solar system almost like a skilled sailor using currents. Voyager used Jupiter's gravity to continue onward to Saturn. This was one of the classic examples of a slingshot maneuver in action. Jupiter's enormous mass and motion made it especially useful for boosting spacecraft outward. That assist helped Voyager continue a journey that would transform our understanding of the outer planets. NASA notes that a spacecraft can typically gain several % of its speed in a well-planned slingshot flyby. Even a few % can make a major difference in interplanetary travel. Over long distances, that added speed can shorten travel time or make farther targets reachable. Small advantages in orbital mechanics can produce huge practical results. The closer a spacecraft passes to the assisting planet, the larger the gravity assist effect can be. A nearer pass allows the planet's gravity to bend the trajectory more strongly. Of course, such close approaches must also be carefully controlled for safety and mission goals. Precision becomes especially important when using gravity in this way. Solar Orbiter uses repeated Venus flybys not only to change speed, but also to tilt its orbit for better views of the Sun's poles. This is a more subtle use of gravity assist than simply gaining speed. By adjusting the angle of the spacecraft's orbit, mission planners can reveal regions of the Sun that are otherwise difficult to observe well. Gravity can therefore reshape not just how fast a spacecraft moves, but what it is able to see. ESA reported that a February 2025 Venus flyby increased Solar Orbiter's inclination from about 7.7 degrees to around 17 degrees. That is a significant change in viewing angle for a solar mission. It helps open a new perspective on the Sun's polar regions, which are important for understanding solar activity and magnetic behavior. A single flyby can make a spacecraft scientifically more powerful. A later Venus flyby is planned to raise Solar Orbiter's inclination further to about 24 degrees. This gradual shaping of the orbit shows how missions can build up their final geometry step by step. Rather than forcing one huge change all at once, planners often use repeated gravitational encounters. It is a patient and efficient way to reach a specialized orbit. Lucy has used Earth gravity assists to help it reach its Trojan asteroid targets. The Trojan asteroids share Jupiter's orbit around the Sun and are spread across a wide region of space. Reaching them efficiently requires careful trajectory design. Earth's gravity became one of the tools that helped launch Lucy toward that distant scientific journey. OSIRIS-REx also used an Earth gravity assist on its route to Bennu. That flyby helped place the spacecraft onto the correct path for rendezvous with the asteroid. Even missions to relatively small and nearby targets can benefit from planetary flybys. Gravity assists are useful across many scales of exploration. Lagrange points are positions where the gravitational effects of two large bodies combine in a useful way. At these locations, a smaller object can maintain a special orbital relationship with the larger bodies. These points are not places where gravity disappears, but places where gravitational pulls and motion can work together in a stable or semi-stable pattern. They are some of the most useful destinations in spaceflight. In the Sun-Earth system, there are 5 Lagrange points. Each one has a different arrangement and different practical value. Some are more stable than others, and some are better for certain kinds of spacecraft. Together, they show that gravity can create structured regions of balance in an otherwise enormous and open space. At some Lagrange points, spacecraft can remain in favorable positions with relatively low fuel use. This is one reason these locations are so attractive for astronomy and space observation. A spacecraft placed there can maintain a useful geometry without constantly making large corrections. Gravity does much of the work of holding the location. The James Webb Space Telescope operates near Sun-Earth L2, about 1.5 million kilometers from Earth. That is far beyond the Moon, yet still closely tied to Earth's orbit around the Sun. This location provides a stable thermal environment and a good view of deep space. It is one of the best places for a sensitive infrared telescope to work. L2 lets Webb stay aligned with Earth as both orbit the Sun. This geometry makes mission operations more practical and supports continuous communication. It also helps keep the Sun, Earth, and Moon in roughly the same general direction from the telescope's point of view. That arrangement is extremely helpful for thermal shielding. That special geometry helps Webb keep its sunshield between the telescope and the Sun, Earth, and Moon. Because Webb studies faint infrared signals, unwanted heat must be blocked very carefully. The sunshield acts like a permanent shade, protecting the observatory from warming. Gravity and orbital design make that protective setup possible. Webb launched on December 25, 2021, and arrived near L2 on January 24, 2022. That journey was not simply a straight trip to a parking spot, but a carefully planned transfer into a special gravitational environment. Reaching the area near L2 required precision in speed, direction, and timing. Orbital mechanics turned the launch into a controlled arrival at a very delicate destination. Gaia also operated near Sun-Earth L2. This made sense because Gaia's mission required stable observing conditions to map the stars with extraordinary precision. Working near L2 allowed it to scan the sky while maintaining a favorable environment. Gravity again helped create a quiet observational platform. ESA lists Gaia's launch date as December 19, 2013. From there, it traveled into its operating region near L2 and began a mission that would transform astronomy. By measuring stellar positions, motions, and distances with extreme precision, Gaia created one of the most important star maps ever made. The success of that mission depended partly on the stable orbital conditions near L2. ESA says Gaia ended science observations on January 15, 2025. By then, it had spent years measuring the Milky Way in extraordinary detail. Its long mission helped astronomers better understand the structure, motion, and history of our galaxy. A carefully chosen gravitational location supported one of the most precise surveying efforts in astronomy. L4 and L5 are special among Lagrange points because they are resistant to gravitational perturbations. In simple terms, objects near them tend to stay there more naturally than at some other Lagrange points. Small disturbances do not immediately send them away. This makes them especially interesting both scientifically and practically. Dust and asteroids can accumulate near the stable L4 and L5 regions. In some planetary systems, these areas can gather swarms of small bodies, known as Trojan asteroids. They are held there not because gravity stops, but because gravity and orbital motion create long-term stability. These are natural storage zones shaped by celestial mechanics. ESA compares the stability of L4 and L5 to a ball resting in a large bowl. If the ball is nudged a little, it tends to roll back toward the center rather than fly away. That image helps explain why these regions are considered stable. It is a useful and simple picture for understanding a subtle gravitational idea. Some spacecraft use halo orbits around Lagrange points rather than sitting exactly at the point itself. These looping paths can provide operational advantages, including better thermal conditions or communication geometry. A halo orbit still takes advantage of the gravitational environment while avoiding some practical limitations of the exact point. It is a graceful example of using motion within balance rather than balance without motion. Robert Farquhar helped place ICEA 3 into a halo orbit around a libration point between Earth and the Sun. This was an important step in showing that these special gravitational regions could be used in practical mission design. Instead of thinking of space as empty and structureless, missions like this showed that gravity creates pathways and neighborhoods that spacecraft can use. It was a quiet but meaningful advance in the art of moving through space. Gravitational waves are ripples in space-time itself. They are not waves traveling through air or water, but tiny distortions in the structure of the universe. When very massive objects move in extreme ways, they can send these ripples outward across vast cosmic distances. By the time they reach Earth, the effect is incredibly small, but still real and measurable. Einstein predicted gravitational waves in 1916 as part of his theory of general relativity. For many decades, they remained a theoretical consequence of the equations rather than something directly observed. Scientists believed they should exist, but detecting them required technology of extraordinary sensitivity. Their eventual discovery became one of the great confirmations of modern physics. Accelerating massive objects such as orbiting neutron stars or black holes can generate gravitational waves. The stronger the masses and the more dramatic the motion, the more powerful the waves can be. Some of the strongest signals come from pairs of dense objects spiraling toward each other before merging. These events allow gravity itself to carry information across the universe. Gravitational waves travel at the speed of light. That means they move as fast as any signal can move through the universe according to modern physics. This connects them closely to the deepest ideas in relativity. Even though they are generated by gravity, they still obey the same cosmic speed limit as light. As a gravitational wave passes, it stretches space-time in one direction and squeezes it in another. The effect is tiny, far smaller than the width of an atom when measured across large instruments, but it follows a clear pattern. This is what detectors are designed to sense. Rather than seeing a distant event with light, scientists can feel its faint geometric pulse. LISA will extend gravitational wave astronomy into lower frequencies than ground-based detectors can observe. Some cosmic events produce waves too slow and broad to be captured well on Earth. By moving the observatory into space, scientists can study a different range of gravitational signals. This will open a quieter, deeper part of the gravitational wave universe. ESA's LISA mission will use 3 spacecraft. These spacecraft will fly in a carefully arranged pattern, forming a giant triangle in space. By measuring tiny changes in their separations, the mission will act like an enormous gravitational wave detector. It is a beautiful example of using formation flying and precision measurement together. LISA will detect waves by measuring tiny distance changes between free-floating test masses with lasers. When a gravitational wave passes through, it changes the distances between those masses by an incredibly small amount. Lasers make it possible to track those tiny changes with extraordinary precision. In this way, gravity becomes something that can be measured by its effect on space itself. LISA Pathfinder demonstrated that test masses could be kept in near-perfect gravitational freefall in space. This was an important technical success because LISA depends on measuring delicate effects without unwanted disturbance. The mission showed that spacecraft systems could shield the test masses from many outside influences. It proved that the quiet conditions needed for future space-based gravity measurements were achievable. Hubble measured the deflection of starlight by the gravity of a white dwarf, directly testing Einstein's theory with a stellar remnant. This was important because it showed that even the light from a distant star can be bent measurably by the gravity of a compact object. The effect was subtle, but modern instruments were precise enough to detect it. It was another gentle confirmation that gravity curves space-time, just as relativity predicts. A close planetary encounter with a white dwarf can be extreme because the star's tides are very strong. Even though a white dwarf is not as extreme as a neutron star or black hole, its mass is packed into a small volume. That creates steep differences in gravity across nearby objects. If a planet passes too close, it may be torn apart by those powerful tidal forces. Pulsar pulses can repeat with remarkable regularity, from milliseconds to seconds. This makes pulsars some of the most precise natural clocks known. Their steady timing allows scientists to study many subtle physical effects, including gravity, motion, and the influence of nearby companions. In a universe full of chaos, pulsars can behave with astonishing rhythm. A pulsar's magnetic field channels particles along the magnetic poles, helping create its beams of radiation. Those beams do not shine evenly in all directions. Instead, they are focused into regions linked to the magnetic geometry of the star. As the pulsar rotates, the beams sweep through space and can pass across Earth like a lighthouse beam. Pulses are seen because a pulsar's magnetic axis is often tilted relative to its spin axis. If the two axes were perfectly aligned, the sweeping beam would behave differently and might not produce the familiar pulse pattern. The misalignment allows the beam to cross our line of sight again and again. That geometry turns rapid rotation into a regular signal. Pulsars possess some of the strongest magnetic fields known. These fields are far beyond anything humans can create on Earth at large scale. Combined with the star's extreme density and fast rotation, they produce extraordinary physical conditions. Pulsars are therefore important natural laboratories for studying matter, magnetism, and gravity together. The event horizon of a black hole is not a solid surface like the surface of a planet. There is no hard crust or boundary you could stand on. Instead, it is a limit in space-time beyond which escape is no longer possible. This makes black holes strange not just because of their strength, but because their most famous boundary is not made of ordinary material. Astronomers usually classify black holes as stellar mass, intermediate mass, or supermassive. These categories help describe how large they are and often hint at how they may have formed. Stellar mass black holes come from collapsing massive stars, while supermassive ones live in galaxy centers. Intermediate mass black holes remain rarer and harder to pin down. NASA notes that cosmologists also suspect a possible fourth class, called primordial black holes, formed in the early universe. These would not come from stars, but from conditions shortly after the universe began. Their existence is still uncertain, but the idea remains scientifically interesting. If found, they could teach us about both gravity and the earliest cosmic history. Intermediate mass black holes are much rarer and harder to identify than stellar or supermassive black holes. They sit in a middle range, where evidence is often less direct and harder to interpret. Finding them matters because they may help explain how the biggest black holes grew. They are a missing piece in the story of gravitational collapse across scales. Some intermediate mass black holes may form through collisions and mergers of smaller black holes. In dense star clusters, repeated encounters and mergers can gradually build something larger. If this process happens often enough, it may produce black holes between the familiar stellar and supermassive ranges. Gravity, once again, may build larger structures from repeated smaller events. Supermassive black holes can power enormous jets seen in some galaxies. These jets can extend across huge distances and are driven by matter falling inward and releasing energy in the black hole's environment. The black hole itself does not shoot material outward from inside the event horizon, but the surrounding system can generate powerful outflows. Gravity at the center helps energize activity on galactic scales. Hubble and radio observations of Hercules are show jets driven by gravitational energy from a supermassive black hole. Material falling inward toward the black hole releases immense energy, and part of that energy helps produce these dramatic jets. The system demonstrates how something associated with darkness can indirectly power brilliant, far-reaching structures. A black hole can therefore influence a galaxy far beyond its immediate center. Black holes can also reveal themselves through tidal disruption events when they tear apart stars. If a star passes too close, the difference in gravitational pull across it can stretch and shred it. Some of the torn material falls inward, heating up and glowing brightly. These events let astronomers notice black holes that might otherwise remain hidden. Hubble uses gravitational lenses to study galaxies, stars, exoplanets, and dark matter. Because lensing depends on gravity rather than emitted light alone, it can expose objects and structures that would be difficult to study otherwise. It also allows astronomers to measure mass in ways that ordinary imaging cannot. Gravity becomes both the subject and the instrument of discovery. Gravitational lenses can act like natural telescopes, revealing very distant galaxies. A foreground mass can bend and magnify the light from a much more distant object behind it. This allows astronomers to see farther back into cosmic history than they otherwise could. The universe, through gravity, sometimes helps us observe itself. A distant gravitational lens can also be used to estimate the mass of the foreground galaxy doing the lensing. The amount and shape of the bending depend on how much matter is present and how it is distributed. By studying the lens, scientists can weigh a galaxy from far away. It is a quiet and elegant method of measuring something too large to place on any ordinary scale. Euclid discovered a nearby Einstein ring in 2025, showing that strong lenses are rare but extremely useful scientifically. A system like this provides an unusually clean example of how gravity bends light. Because the alignment is so special, the resulting structure contains rich information about the lensing mass and the background source. Rare systems can therefore become especially valuable. Like dwarfs, neutron stars, and black holes, all show that stronger gravity can exist when matter is compressed into smaller volumes. A body does not need only more mass to become more extreme. Concentrating its mass more tightly can change gravity dramatically near its surface or boundary. These objects form a kind of sequence of increasing compactness. They teach us that gravity depends not just on how much matter exists, but on how densely it is packed. Stellar remnants show that gravity depends not only on total mass, but also on how concentrated that mass becomes. A spread-out object and a compact object can have very different gravitational effects near them, even if their masses are related. This is why a white dwarf, neutron star, and black hole can feel so different from an ordinary star. Density and size matter deeply in gravitational behavior. The Sun's gravity influences seasons, eclipses, and lunar phases by controlling motion in the Earth-Moon system. Earth's yearly orbit around the Sun shapes the seasonal cycle, while the Moon's orbit relative to Earth and the Sun shapes the phases and the possibility of eclipses. These familiar patterns in the sky are not random. They are the visible result of gravitational relationships. Total solar eclipses are possible on Earth because the Sun is about 400 times wider than the Moon, but also about 400 times farther away. That remarkable geometric coincidence makes the two objects appear nearly the same size in our sky. As a result, the Moon can cover the Sun's bright disk almost perfectly during a total eclipse. It is one of the most striking examples of scale and distance working together in astronomy. That geometric coincidence makes the Sun and Moon appear nearly the same size in Earth's sky. If either their sizes or distances were significantly different, total solar eclipses would not look the way they do. This matching is not a law of nature everywhere, but a special circumstance of our system. It gives Earth one of the most dramatic sky events known. A total solar eclipse occurs when the Moon's orbit carries it into just the right alignment to hide the Sun's disk. The alignment must be precise because the Moon's orbit is tilted and does not line up perfectly every month. When everything does match up, day briefly becomes shadowed and the Sun's outer atmosphere can be seen. It is a calm reminder that celestial mechanics can create moments of extraordinary beauty. NASA notes that some total solar eclipse occurs somewhere on Earth roughly every 12 to 18 months. They are not rare on a global scale, but they are rare for any particular location because the path of totality is narrow. This means eclipses happen regularly, yet still feel special whenever they pass overhead. Gravity and orbital alignment quietly schedule these events. The Moon's gravity also tugs on Earth's mantle, not just the oceans. This means tidal effects are not limited to water. Even the rocky interior of Earth responds slightly to gravitational differences. The whole planet, in a subtle way, participates in the lunar tidal rhythm. Gravity can be measured from space to monitor changes in water and ice on Earth. When large amounts of mass move, such as melting ice sheets or shifting groundwater, Earth's gravity field changes slightly. Satellites can detect these tiny differences. Gravity thus becomes a way to observe environmental change across the planet. Grace mapped tiny variations in Earth's gravity field to track mass movement across the planet. By following small changes over time, the mission helped scientists study ice loss, water storage, and other important Earth system processes. This is a beautiful example of gravity being useful not only for astronomy, but for understanding our own world. Subtle changes in pull can reveal hidden movement of mass. Exoplanets very close to their stars are often expected to become tidally locked. Over time, the star's gravity can slow the planet's rotation until one side always faces inward. This process is especially likely when the orbit is tight and gravitational effects are strong. Many distant worlds may therefore have permanent day on one side and permanent night on the other. On a tidally locked world, one hemisphere can have constant daylight, while the other has constant darkness. This creates a very unusual planetary environment compared with Earth's rotating cycle of day and night. Temperatures, winds, and clouds could behave in dramatically different ways on the two sides. Gravity can therefore shape not only motion, but also daily experience on the world. NASA notes that hot Jupiters are tidally locked in most cases. These giant planets orbit very close to their stars, so strong tidal forces act on them. Over time, those forces are expected to synchronize their spin and orbit. That means the same side of a hot Jupiter usually faces its star continuously. For hot Jupiters, tidal locking can produce different cloud patterns on the day side and night side. The side facing the star receives intense heating, while the far side remains much cooler. This can drive unusual atmospheric flows and create different conditions across the planet. It is another example of gravity shaping weather in distant places. NASA exoplanet research notes that some super-Earths orbit so close to their stars that temperatures may become high enough to vaporize metal. These are extreme worlds where common materials might behave in unfamiliar ways. Their closeness to the star also makes tidal locking likely, and gravitational effects very strong. Such planets remind us that planetary environments can be far stranger than the familiar worlds of our own system. TOI 561b is thought to be tidally locked. If that is correct, one side likely faces its star all the time, while the other remains in darkness. This would shape surface temperatures and atmospheric behavior in major ways. A single gravitational process can therefore define the basic character of an entire world. If a tidally locked rocky exoplanet has a thick atmosphere, heat may be redistributed enough to warm the night side significantly. Without an atmosphere, the difference between day and night could be extreme. But with a substantial atmosphere, winds and circulation can carry energy around the planet. So tidal locking does not automatically mean one side is unlivable and the other pleasant. The atmosphere matters greatly. Some binary stars are tidally locked to each other, showing that tidal locking is not limited to planets and moons. In these systems, each star may keep the same face turned toward its companion. Gravity can synchronize large, luminous bodies, just as it can moons and planets. The principle is broad and works across many kinds of celestial systems. Tidal effects can heat the interiors of planets and moons by flexing them repeatedly. As gravity stretches and squeezes a body over and over, friction inside can generate heat. This means tides do not only move oceans or slow rotation, they can also power internal activity. On some worlds, this heating can help drive geology and possibly maintain subsurface liquid layers. NASA-supported work in 2024 developed methods to compute tidal effects in bodies whose interiors are not perfectly spherical. Real worlds are often layered, uneven, or shaped in more complicated ways than simple textbook models suggest. Better methods help scientists understand how gravity affects actual planets and moons. Even subtle improvements in tidal modeling can deepen our understanding of hidden interiors. Tides therefore matter not only at coastlines, but also deep inside worlds. They can shape rotation, alter orbits, produce heat, and slowly change the structure of planets and moons over time. Something that seems gentle and familiar on Earth becomes a major engine of planetary evolution elsewhere. Gravity often works quietly, but its effects can be profound. As the night grows quieter, gravity remains what it has always been: patient, steady, and everywhere. It guides the drift of moons, the turning of planets, the bending of light, and the slow balancing of worlds. And while the universe moves in vast and intricate ways, it does so through laws that are calm, consistent, and beautifully silent.